will be better next time I try. And even if I still can't do it, yeah, you know that I'm gonna stick to it. Yes, it's all about going through it, and I'm gonna tell you why. Whoopsie, whoopsies, I made a mistake and it's okay. It's okay. Whoopsies are what it takes to get better and better every day. Whoopsies, I made a mistake and it's okay. It's okay. Whoopsies, help me look, see, I'm better at this today. Woo! Whoopsies, 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 whoopsies.
I'm a little embarrassed when I look at my drawing compared to this. I'm just not getting anywhere with this. It makes me wanna hide. Aw, don't be embarrassed. Don't hide.
You should have seen mine the first time I tried. It took a lot of whoopsies to look this way.
No one's perfect on their first day. Whoopsie.
Whoopsies, I made a mistake and it's okay.
It's okay. Whoopsies are what it takes to get better and better every day. Whoopsie, 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 whoopsie.
Well, what about this? I want to jump rope, but nope, I just can't do it.
Well, not yet. Come on and practice with me. You'll see there's nothing to it.
Whoa! Whoopsie.
Whoopsies, I made a mistake and it's okay. It's okay. Whoopsies, help me look, see, I'm better at this today. Woo!
Wait, was it yeah?
It was only a dream, the waves of evil crashing over us. It was only a weak and faithful scream beneath the battlements. I know it's hard, but for long, before it's too late. Wake up, my love, please don't give up on me. It's hard. Wake up. It was only a dream, the waves of evil crashing over us. It was only a weak and faithful scream beneath the battlements. But I know it's hard, before long, before it's too dark. Wake up, my love, please don't give up on me.
What is up? What is up, you guys? We are back at it again. Day 60 of 100 days of Rootkit. We are, man, chugging through. Taking a break from Python, learning about C, learning about how, hey, all languages are pretty much the same thing. You know, I ain't kidding, all right? I ain't kidding. And you know, learn about maybe just small differences and kind of seeing the insights of differences between object-oriented and non-object-oriented languages. Today we're going to enter Hell. Also, I was able to scour up some of our previous class material, which is 10 out of 10 if you ask me. I dropped it for you guys in the Discord 100 Days Rootkit chat. It kind of got a little buried with messages, but if you scroll up a little bit, you're going to see 2 zip folders there, right? They're going to be containing these files, and I'm going to show those off today. Just we'll quickly go through at least one of them because everything's laid out pretty nicely there. If you are a Discord Premium or a Patreon member, I will be dropping later this week these documents again in there in the supporters chat, but with documentation. All right, so you get that extra level of knowledge. So continuing on here, let's go ahead and finish up with our intro. If you didn't know, we are Rootkit nonprofit here in the US of A. We are a complete alternative to a college degree. Don't go to college. Just get our cert and then we'll get you a job. Or, you know, what you could do, not go to any other boot camp because they're trash. Absolute garbage. They're going to charge you insane prices. Look, if you want to spend $10,000+ or $100K, look, I'll show you the donate button. All right. In the description, there's a link there. And if you're on Twitch, in the bio, all right, somewhere there, the 100 Days of Rootkit link, all right, click on that. You're going to see this page come up, all right? You can go ahead and send us your entire tuition, all right? Because we're going to teach you literally everything you're going to learn and more, all right? And we can get you a job, all right? You know, if you really want to just give away that cash, you know, here you go. We got you. Don't worry. Don't worry. Moving on here, on top of all the free stuff that we're doing, if you go to the blog section of our site on the week 9, we have our week 9 giveaway going on right now where it's completely free. Anyone can enter it. If you click on the green button here, you can enter the mystery giveaway. I don't even know what the item is going to be. We're all going to pull it together here this weekend and see what it is. It will randomly go to one of you guys. As long as you enter to win, you have to do this every week and just prove that you're subscribed to our YouTube channel, follow our Twitch, etc., etc. Additionally, that link in the bio, if you go there, you can donate. Depending on how much you donate, you can unlock certain rewards like our epic stickers, collab t-shirt, and this epic sweater I got on right here with the Rootkit logo in the back. Super epic, super warm, so warm, I'm dying in this room. It's so hot, I need to open this window, which I'll do after we finish up here. All donations are matched 1-for-1 for the first 10,000 donations, and those roll in at the end of the month. So we should be expecting the matching from the last couple of donations here, either during the stream or slightly after the stream. We'll see. And we have pillars along the way, like streaming for 24 hours straight, shaving my head here live on stream. And the goal, this last one, is our goal not to hit it. So our goal is not to hit the goal, which is shaving my beard here on stream. No one wants to see that. All right, no one wants to see that. No one's here for that. All right, we're here to learn, not to be distracted by me shaving my power beard. All right, my power beard here live on stream. Now we finished the intro. Drop any questions that you have in the chat from the previous day or in general. I'm going to open this window. Give me 1 second. Oh. Whew. Oh, this sweat is so warm. All right. Alrighty, you guys ready for our adventures? Before we dive in and continue what we're doing, I just want to show off what I dropped for you guys. So there's the C101, C102, just generic naming. So C101 is just going to be more of the basic things. If you open that up, specifically if you're on Windows and you have Visual Studio, you can open the .snl, the solutions file that's right the first thing that you see. That will open it up automatically in VS Code and have it laid out nicely. If you're on Mac OS, that's fine. Just an extra clicky step. You got to open up this prepping for 101 file, and here are all your C files and your header files and everything you need. You can just copy this over. These VS files here, you don't need, all right? You don't need these, but the C ones, you can just copy those ones over and you can see what's inside of them and run them for yourself. Since I won the last one, yes, I sent you an email and I added you on the Discord and you haven't gotten back to me. So make sure you email me back or email me right now and claim, because if you don't claim by this weekend, we're going to re-roll your prize. For the donation, yes, I was going to email you about that also for your donation stuff, so we can talk and you can choose a gift that you would like from the amount that you did donate, since you didn't claim anything, if you would like. Or trade them both in for a sweater. Maybe. We'll chat. Email me first, all right? That's the first step. You got to email me so we can start this dialogue. We'll see. I think we can make something work out here, all right? I think we could do this. I think we can make this work out. Just send me an email first. So when you open this up, there's a lot of files. Don't be overwhelmed, all right? We haven't gone over what header files are yet, so don't worry too much about them. The main thing is you want to look for that main function. The main function is what runs the program. Conveniently, we have a file called main.cpp. All right, and that has the main function. And these planes are going to kill me, so we're closing the window. Oh gosh, I didn't close all the way. All right, I'm going to be sweating to death in here. It's going to be a sauna. All right, so in here, you're going to see a lot of functions, and they're all commented out. This is set up really nicely for you to uncomment one, run it, see what it does. Cool, it prints out hello world, and then you can comment it again and go to the next one and see what it does. All right, one by one. And if you want to look in the function more, same thing as in VS Code. If you hold down Control, you'll see this turns in, I'm hovering over it right now, not holding Control. Now when I press Control, it turns into like a link. If you click on that, it will take you to the function and you'll see the actual lines of code in here. And you'll see what they're actually doing. So in here, we have a bunch of examples everywhere. So this printing string formatting will have examples of how to do backslashes, tabbing, backspace, character returns, double quotes, single quotes, just a bunch of crazy shenanigans. Excuse me. And it is pretty in-depth. It shows you everything that you really need to know for the beginnings of C development. So I guess we forgot to go shorts. Shorts are going to be integer values, but if integers are 4 bytes long, shorts are going to be 2 bytes long, so half the size. We went over most of these already. Talked about our strings. We talked about printing them out. So this is just showing you different ways you can go about printing these out. There is a %d, which we didn't go over, which you can use. I think it's best to stay as specific as possible, but D is going to be for any type of decimal value. Let's see here. To print out hex, you can do HHC, I believe. I'm trying to, is it HHC? I feel like it's, no, that's a half. Is that? I would have to look it up, but you can also look it up looking through these and see what exactly these will help you with or what they can be utilized for. Let's see here. So we got the variables. There's printing examples, which these were the printing examples. There's a bunch of variable examples and some that we didn't talk about specifically. like these guys right here, which are going to be defined values, which will tell you things like what's the minimum value a character can hold, maximum, min and max of a short value, of an unshort, int, long, a long. You can basically see the min max number for each one of them. And there's a couple examples that came up in my head that we didn't show off. So we're going to be probably matching this stuff, going over all of the logic that you can do. This shouldn't be anything new, except for exclamation mark is what you do for not instead of the word not. Switch statements, which are like if statements, slightly different, but they function very similar to if statements. Of course, you got your if statements, and then your elifs, your else statements, and then different ways to input. So we talked about scan F, and then if you're in Windows, you're using scanf_s for the more secure version. There's get char, and then we didn't talk about this other way, but there's also fgets. Like I said, there's a million different ways to get input from the user. All right, so don't really worry too much about all of these. I believe fgets is generally regarded as a more secure way to get input from the user than scanf if you're not on Windows machines, because you don't have access to _s. Mostly because you have to specify exactly how much data you want to get in, right? Get in from the user. Let us see here. So this is really great. And then 102 obviously goes more into depth. Something that we also didn't hit on yet was structures. So you can kind of peek in structures. I don't think there's very many examples about structures at all in here. I think that was just left in, and it's mostly in 102 where you'll see examples of structures, which we'll get into in a bit. But yeah, super good file for you guys to utilize, look through, and mess with. All right. So let us continue, shall we? I'm gonna go ahead and close this out. Actually, let's use in 102 the pointers file. Here we go, our good old pointers. So what are pointers? Why are we talking about pointers? Why do they keep getting brought up? Why do I have a feeling I'm going to get cancer for it? Why is it being brought up that we might get cancer from it? Great questions all around. Great questions all around. Let's go ahead and comment this stuff out here. And let's take a look here. But I guess before we go into our look, let's just recap variables. All right, variables. We've seen this before, right? We've seen these variables. Short is a new one. Again, that's just half the size of a normal integer value. All right, that's why you can have a short or an unsigned short. It's just like an int and an unsigned int, just half the amount of data. All right, you can print those out. And if we go ahead and run our main here, we'll get this nicer printout. Can I don't think these properties will persist, but you know, I'll do it anyways to see if I can help you guys out a little bit. Hopefully they persist. I don't think they will persist. There we go. So hopefully that's a little easier for you guys to see. Let me shrink this down. Please. Come on. There we go. So, I mean, nothing new. This is just telling you the size of each one of these variables. So shorts are going to be 2 bytes in size, ints 4 bytes in size, longs 4 bytes in size, longs 8 bytes in size, floats 4 bytes in size, doubles 8 bytes in size, chars and bools are going to be 1 byte in size, depending on how in what operating system you are in. It will be 1 bit in size. It just may show up as 1 byte when you measure it. All right. Additionally, you can see here the minimums and maximums for all these values. So chars are 1 byte. All right, 1 byte in size, which means they can handle up to, that's right, 0 to or 256 values. 256 values. And if it's assigned value, it's going to be, of course, negative 128 to positive 127. If it's not signed, it goes up from 0 to 255. In total, that's 256. And then you can see here what the max is for integers, longs, and double longs. All right. So it's very important to know what these are, because if you're making an application that will be counting very high, you want to make sure you're not running into issues here where you're going over these values. Because if you go over these values, you're going to have things turn over. All right. You're going to have them turn over. So what does that mean? It's going to go from the very, very high value. If it's an unsigned integer, for example, it's going to go up to its maximum value right here. So if this is an unsigned integer, you're going to go up to here, and then bam, you're going to go back to 0. If you add 1 to this number, it's going to roll over back to 0. All right. We kind of showed this when we did our binary math. This number should look very familiar to you. For your unsigned short value, to 65,553. Why should this look familiar to you? This is the max port size you can have. Remember ports? Should remember ports. It's going to be on the test. Ports can be between 0 and 65,553. They are literally assigned a short value, and that's why that's the maximum for ports. All right, because it has a short value assigned to it. All right, so you'll see a lot of common things like your chars here. Again, 255. You'll see this a lot. RGB. If you're messing with RGB settings, all right, they usually go up to 255. It's not a coincidence. It's not because someone plucked that number out of thin air. No, it's because of the underlying code and its limitations. All right, because of its limitations. Any questions on this before we chug on forward here? So you can refer to this code, and these are how you can get the min and max values out. So if you don't remember them, you can always look them up. If you don't want to look them up, you can always do this. This is very nice because, again, so utilizing these can be very convenient depending on what you're doing, because again, every operating system is different. All right, you're not guaranteed that integers will be 4 bytes in size or longs will be 4 bytes in size. They may be different on different operating systems. So utilizing this, these depends. These are very specific use cases. You may want to utilize things like this to make sure you're not accidentally rolling over your numbers, right? Super useful file. Yes, this is a very super useful file, all right? When I'm doing live demos like this, we're definitely live. That's all I gotta say. All right. This is more of the line what we usually do for our normal scripted teaching events. All right. So we seem a little more put together for our corporate partners. All right. Don't really want to do a on the fly live demo for corporate partners that could be paying a good amount of money for your training. Not sure where you got those files that you're going over. Are they? Yes, Kamal. They're all posted in the 100 Days of Rootkit channel. We made these a while ago when we did our C intro to C classes. So they're in the 100 Days of Rootkit. They're going to be reposted in the supporters chat for those of you who are supporting, with a bunch of comments and documentation. All right. So it's a little bit easier. There's some light documentations here that you can mess with, but don't worry too much about it. So the main thing is we're looking at our variables here, all right? Nothing new that we've seen so far. These are variables. You got data, you shove the data in it. It's just a placeholder. Printf is weird. Yeah, I know, you gotta do the percent sign, whatever, all right? Nothing crazy. So let's get a little crazy, shall we? There's this concept of pointers, all right, in programming. It's everywhere in programming, right? It's everywhere in programming. It's just not done in a lot of new programming languages. You don't mess with it directly. You do kind of mess with it when you mess with lists in Python or arrays in JavaScript or dictionaries. You are messing with them, but you don't really know you're messing with them. The most you guys have messed with them would be in regards to functions. Remember how in Python, if you just have a function without the parentheses, you don't actually activate or execute or turn it on. It's just kind of there. If you print it out, you'll see that 0x and long number. That's the hex value for it. But what is that hex value for? Why is it even there? Who made it up? Great question. Those are going to be the pointer values that point to where that code is in your memory right now, live, just in your RAM. That's the exact address for it. Just like how you have an address at your house, you know, how to get there. That is the address to get to where that code is stored in your memory. It points to where that code is. It's called a pointer because it just points. It's the address to where something lives, to where it exists. Functions are not the only ones that have this. All variables in every language have pointers because you have to point to where this data even is in the first place. How does your computer know where your variables are living and which variable is what? All right. Well, it's laid out kind of like a book. All right. Table of contents in your book tells you where to go to get to a certain page, a certain chapter. It's the same thing in computers. And the table of contents would be, for example, your variable's name. And then after that, you usually see the page number. Instead of a page number, that's going to be the pointer's value, right? It will be the pointer itself that tells you where to go in memory in order to get that data, all right? Very important for us to know this before moving forward. So let's bring up Paint, all right? Pointers, again, are going to be referencing in memory where your variable is or where your function's code lives, where your main is at in memory. Because we got our, remember we got our stack and we have a heap, all right? All of your code that you've made and produced so far is going to live up here in the stack. Anything that you statically define in your code is going to be living here in the stack, all right? This kind of gets more blurry when you're dealing with other languages like JavaScript and Python because you don't really have as much control over this. But when you're in C, you have control over everything. Everything we're doing right now will be in the stack. So when we want to get a pointer, it will tell us the address. It's best to think of this as just one address space. It gets a little bit more complicated than this though, because your operating system has ALSR, is that the right acronym? Basically address randomization, because it's very exploitable if you can just easily label everything as, you know, here's hex value 0 and here's hex value F. Oh, that was a weird F. F for a very long time. Hackers can potentially figure out where everything is because memory is laid out for everyone's computers the exact same way. Servers' memory is laid out the exact same way as yours. So there's no real difference. So operating systems will employ techniques to mitigate memory-based attacks with randomization. So your operating system itself will actually see memory in this raw form where it goes from address 0 to the max address size, right? To the max address size. But applications will not see this. They will be randomly placed somewhere and they will be given their own little minor 0x to 0f little memory space. All right? It's kind of like VPNs and VLANs, which we've talked about, where you take a real physical network and you split it up into more little tiny networks. It's exactly the same thing that happens in your operating system, all right? Now, page numbers, all right, in a book, 1, 2, 3, 4, 5, 6, etc., all right? It's numbers. I know, math, numbers. Look, if you want to read a book, you got to know the numbers, all right? It's the exact same way in memory. You can translate this to decimal values, so 1, 2, 3, 4, 5, all the way to 10, and then back to 1. We use hex because it's more condensed, and it translates easier from binary data to hex, all right? It's easier for that one-to-one translation. If you remember from our class over how to do the conversion between binary, octal, and hex, it's very easy to move between those compared to going to decimal, which is a little bit more of a pain, all right? So everything's going to be in hex, but it's the same, just like a book and a page, right? So every variable has a pointer attached to it. So in this example right here, it's we have a variable, an integer value called myInt. You've seen this before. We're just putting 10 inside of it. We're just putting the value 10. And when we want to print the value 10 out, we've seen how to do that already. We just say %d or %i is what we've traditionally seen so far. And then we say the variable, right? We just say the variable's name and it will print out what our variable is, all right? All variables have a pointer attached to them because remember, there's a table of contents effectively at the beginning of your code that says the variable's name and then what page it lives on. That page it lives on is your pointer, and you can extract that information out of your variable here inside of C. You can do that with the ampersand. So we saw that a little bit earlier. I told you guys not to worry about that till we got to pointers. Now we're here. Now we're going to learn about it. The ampersand sign in front of your variable is the way to get the pointer for that variable. So what page in memory does that variable's data exist? All right. So if we print this out, so you're going to see when I run this, we're going to see the value of our variable, which is going to be 10, nothing new there. But we're also going to see the address of our variable. So what the pointer is, where it's actually physically located in memory. If you could shrink down to a very, very small size and jump into your RAM and walk all the way to that location, you would physically see it there, all right? And then we're also going to print the size of the pointer value, all right? And I'll explain that here in a second also. So if I run this, you're going to see that the value is 10, like normal, right? And the pointer for our variable is this address. This is where the value 10 lives. This is, if we scroll our book and get to this page, on this page we'll see 10 written on the page, all right? Because the value 10 lives on this page in memory, all right? And pointer sizes are going to be 8 bytes in length, right? 8 bytes in length. Any questions on this so far? Anyone can guess why the pointer's value is 8 size in length. It's very, very important. Any guesses? You guys got 10 more seconds, all right? Before I reveal the answer here. We've talked about it before, all right? We've talked about it before. We're going to be stitching this stuff all together, right? It's the reason why we went over foundations first, and then we're going into this stuff later, so you can kind of understand the base. We can stitch it all together now, all right? If we pull up our trusty calculator, because we don't know how to do math ourselves, all right? We use calculators, all right? Why wouldn't we? I don't live in the ancient old days where I have to bring out a pencil and pen, all right? Calculator. If we do 8, and how many bits are in a byte? That's right, 8. If we do 8 times 8, we're going to see a magic number here. 64. What else is 64? What's significant about 64? Any guesses in regards to this? All right. I'll give you guys 10 seconds here. The significance of 64. It's divisible by 2. Oh, man. Come on, come on. Sometimes you're on top of it, man. And sometimes you give me that dumb shit. No, come on, you guys. I need you guys to guess a little bit on that. We're on 64-bit computers, right? There's a reason why this is 64. Why it's 8 bytes. Because our computers are 64-bit machines. Usually, all right? You can get a 32-bit machines. This is not a coincidence. This is everywhere in your computer. Your CPU will process up to 64 bits of information every cycle. Additionally, if it can only handle up to 64 bits of data at once, your CPU can only do lookups based off 64 bits of data. So your RAM will be or will allow for up to 64 bits of address locations. All right. We talked about in 32-bit computing, there was a big limitation that most of our phones are actually out compute, all right, or higher spec than it. 32-bit computers can only allow up to 4 gigs of RAM on that device. It was 4 gigs RAM, right? I'm pretty sure it was 4 gigs RAM. I'm pretty sure I questioned myself last time when we talked about this too. Most of your phones will now, the higher end ones will actually have more than 4 gigs of RAM on your phone. This is a limitation not on the CPU. Well, it's the CPU's fault for half of it, all right? The other half is the RAM providers, because your address spaces can only be up to 6 or 32 bits in size. So remember when I said in here that you can have, the beginning of your memory is going to be address size 0, and the ending is going to be, F super long. All right. That ending value is going to be in 32-bit computers up to 32 bits of size of Fs. All right. That's the max address you can have. For 64-bit computers, this now doubled. So now you can have up to twice as much in F values. Now you guys most likely won't be running the maximum size of RAM your computer is allowed to utilize. All right. How many pages it can have in its RAM. All right. Which I think is like a couple terabytes. You guys will have to look that one up. But this directly affects how much RAM you can run your computer, because you cannot run more than what your system is purely capable of, because your CPU cannot look things up that are larger than what it can handle processing at any certain cycle. So again, that is why you'll see your pointer values will be of size 8. So if all of this were Fs, that means we were at the maximum memory location. If we had the maximum amount of RAM, which we don't, because my computer only has like 32 gigs of RAM. So I'm guessing this would be the max value right here. So we might see Fs starting from here all the way down, and that means we've reached the end of my memory in my computer, I'm assuming. All right, so we wouldn't fill up the rest of these because we physically don't have enough pages in our RAM to look through everything. All right. So, important concept. Any questions right now in regards to pointers? Any questions right now in regards to pointers? Please ask them, because we're about to go 0 to 100 very, very quick here. All right. As long as you know this concept and you're fine with it so far, you should understand what we're about to explain next. But if you're a little shaky on it at all, please ask a question, because you definitely won't understand what's about to happen. Twitch is hella glitchy right now. Then you can come over and join us on YouTube. All right? Where all the cool people are at. "30-second break real quick before we take off." You got 30 seconds right now. Better write those notes. Ask any questions. But again, these are all important. Make sure you guys rewatch the older days if you don't remember these things. You need to know these things. This is important because even if you're in Python programming, this is still happening under the hood. And you may have to interface with this in Python eventually. There are limitations to Python because of this underlying stuff. If you want to speed up things or you don't know why something's being slow, it's probably because of these underlying concepts. It's very important you know this stuff. All right? Very important. All right. I think that's been about 30 seconds. So let us continue on here. This was a while ago. Okay, so Twitch is all good now. All right. So let's continue on. All right, let's continue on our journey here. So let's look at this next example we got. And if we do control and click on it, it will take us here. Every variable can have a pointer equivalent. This gets a little, all right, this is our first downward spiral to potentially being confusing. You can imagine a book, all right? A book that's, made by a crazy person that wants to just make you feel like you're living in the Matrix, all right? So we open up this book. Hold on, let me go grab a book. Get some examples here. What an appropriate book, all right? Algorithms with C. All right, beautiful book here by O'Reilly. O'Reilly is absolutely beautiful. I wish they stayed up with the times because I'm pretty sure they're slowly dying out because no one's really going around buying books anymore. They want to see videos or audio versions of stuff. So hopefully they get with the program. We'll see here. So we got this book. I go to the beginning, right? I go to the beginning of this book, right? And at the beginning of this book, I got my table of contents. So we know already, let me put something here to keep the placeholder. If I make a normal variable called int myvar and equal that to 10, what we're doing here is we're saying we are creating a page maybe in the middle of this book somewhere. And we're putting the value 10 in the center of this, all right? Now we need to also modify the beginning of our table of contents here to point to where that var is, all right? And that all happens automatically for you instantly when you write this line and your computer compiles it, right? This isn't anything new. Your value gets stored in memory, and then something is put in the table of contents of your RAM effectively that will be pointing to what page this value is at, right? Makes sense so far. This is the Inception version where it's the same. You have a table of contents that it says my void, and that will have a page value, a pointer that points to a page. The difference is you're pointing to a page, and on that page, it will actually be pointing. It will say, "Hey, fooled you, idiot. Go to this other page instead." All right? Your table of contents has a pointer that points to a pointer that points to some data. All right? It's a two-step process. All right? It's a two-step process. It works exactly the same. You go to your table of contents. That takes you to a page. The page says, "Gotcha, idiot. This isn't what you want. You want to go somewhere else." All right? And it will tell you where to go next. All right? Little bit of a search that it makes you do. right? A little bit of a search it makes you do, but you can still find where that data is and get that data and mess with it, all right? Any questions on that? Any questions on that? Please ask, all right? Please ask if you have any questions, all right? So we can see here if we print this or run this, well, we're going to see that we're printing out our values, all right? Our table of contents values, all right? Our pointers here. And they have a lot of beef with us, I guess, all right? You'll also see this will be in order because your computers like things being laid out nicely and organized. So guess what? It's going to be as organized as you think it's going to be. This value is going to be made first, and it's going to be laid out before this one, which is laid out before this one, and laid out before this one, etc., etc., etc. And you can potentially use this information to figure out how large each value is. All right, how large each value is. Let us see here. Any questions before we chug on forward here? I mean, it doesn't make you watch it, but you're more than free to join, all right? So you're going to see something kind of weird going on here. In these values, you're going to see it jumps, or typically will be jumping, all of these are going to be jumping 2 bytes, right? 2 bytes in values. No, it's jumping a little bit more than that. All right. The reason why it's at least doing 1 byte is because you have a pointer that's pointing to pointer data. So one is your pointer itself is going to be stored somewhere, which is what we're printing out, and it's going to be 8. And then after that, you're going to have some data somewhere that it's going to be waiting for that's going to be 8 in size. Let's not read into this too much for right now, but this is, you'll see it's all laid out organized wise. All right. Let's see. Right here, we're just printing the OG pointers for each one of these values, right? For each one of these values. We'll get into use cases here in a second. It's very valuable, the use cases for pointer. Very, very, very valuable, especially for keeping things small and efficient and effective, all right? So let's go to our next example here. Pointer space saving. So I guess we're going right into one of the pros, right? If we click on this, pointers can help us save space, save memory, all right? Save memory space. We can make programs that are smaller than is currently possible with pretty much any other language that doesn't let you do pointer manipulation. You can keep things very, very small. You can make your program potentially dynamic. You can have it alive. You can have it mutate. All right. So you can make self-mutating programs. What does that mean? Where your program actually rewrites itself as it executes. All right. This can be done for good purposes. You can do this also as a way to make your virus always changing and undetectable to antivirus systems. All right. There's a million different reasons why pointers can be the most epic thing. All right. So for space savings, all right, let's see here. We got our variable here called myInt, which is going to have 10. And then we have something called myPointerInt, right? Something called myPointerInt. So we know this is a pointer because we're declaring it with an asterisk, all right? We saw that before up here. The asterisk at the beginning means you want this to be a pointer value. You'll also see, at least in VS Code, if you hover over it, you'll see there's an asterisk there, which means that it's going to be a pointer value. Now, I just clicked back. I don't know where, hold on, let me click on this again because I forgot where we are. Here we go. So pointer values can only accept pointer value data. What does that mean? Well, if you say something is a pointer, that is going to be a page of the book. That means it's supposed to be a page of the book. It's expecting data that's going to be pointing at a page in the book. So you can't just say my pointer int is going to be equal to maybe 5. That doesn't work. You can't do that because that's not a page of the book. All right, that's not a valid page of the book. That's some data that you're trying to store into it. We also know that with normal variables, they automatically get a pointer generated for us. All right, and the way to access that is using an ampersand. My int. This will give us the pointer for our integer value. This is what we can store in a pointer variable. So if we look here, you can see that my pointer int is going to be equal to the address, the page number, the pointer of my int. What does that mean? What is even going on right now? Why is this even useful? Why is it called saving space? All great questions. What we've done here is we've effectively made 2 rows in our table of contents. One called myInt. You can find it in the table of contents of this book. It will point to a page. When you go to that page, it will say the number 10. Cool. We have my pointer int. My pointer int is the same. It will be findable in the table of contents. It will have an address, a pointer there. When you go to that page will be like, hey, idiot, I'm not actually real data. I'm just pointing you somewhere else. So go to this page instead. The page it's going to redirect us to is going to be the number 10. It's going to be where this data lives. Why? Because we put the address to the number 10 inside of this. All right? Does this make sense right now? Before we move forward, this is important for you guys. All right? We have a straightforward way to access the value 10, and we have a more inception way to access the value 10. All right? By doing this too. All right? This is all part of it. Don't ignore the stuff below right now. We're just talking about these right now. They both are ways to access the value 10. One is just a potentially 2-step process. All right? Kind of scary, but also cool. It is very cool. You can do some really cool stuff with this. All right? I get the myInt equals 10. Can you delve into the other one a bit more? Sure. So let's bring up Paint here. I think this will help to see it a little bit more visual than me pointing at this book in this low quality camera. So we have our variables. Let's say I'm going to do, so I don't have to write as much. I'm going to do X and I'm going to do Y. I know, math, class, flashbacks, PTSD. Stick with me, all right? Stick with me. Forget it. It's just variables. You've seen variables before, all right? This is going to be equal to the value 10. And this is going to be our pointer, all right? I guess I can just do like an asterisk like this. There you go. So what's going on in your computer is you have your RAM in your computer, right? Now, somewhere in here will be a quote-unquote table of contents, right? So in that table of contents, it's going to say that X, when you want to use the X variable, it's going to be at location A, B, and C in your memory somewhere, all right? And you also made Y, So when you look up y, it's going to be at location C, D, and E. Right? These are just the page numbers. Right? So if we're flipping through a book, this is just the page numbers. All right? So we would have to go find page A, B, C. All right? It's a very, very big book. All right? This is the same for both of these. The difference is for X, when we go look for, or on the page A, B, and C, so let's say this is page A, B, and C right here. Right? Let's say this is page A, B, and C. In here, it's going to have the value 10 written in here. Right? The value 10 is going to be in here. Nothing confusing. All right? In C, we can access either the value 10 when we want to use X, or we can also access and look at this pointer here. All right. So every variable comes with two different pieces of data you can look at in C. You can look at the value right here, or you can look at the pointer of it. How you can look at the pointer of it is using that ampersand, like we talked about. All right. Using the ampersand before the variable. Now, Y works exactly the same way. Y, when we say we want to look at the Y value, it's going to be on page CDE. So if we go to page CDE in our RAM, when we look at this page, it's going to say, ha, got you. You need to go to page. And by default, when we first make it, it's not going to have a page number. All right, it's just going to say go to page. And you'll be like, what page? It's going to be like, so you have to tell it what address it's supposed to hold. So in this case, we're telling it that the address of my int, in our case with a picture here, this would be the address of X, is what I want you to hold. All right, so it's going to say, or now it's going to hold A, B, and C, right? It's going to say, it's going to hold the value A, B, and C. So now when you go to Y, Y is going to be holding the value A, B, and C. But additionally, you can use that to go to and follow it to 10, right? It's a two-step process, right? It's a two-step process. It has potentially the access of 3 different value types. It's default to, just like X does, right? X has, let me write this here. X, you can view this with the ampersand. By normally using the variable, you can get this when you're using X, all right? When you're using a pointer called Y, you can access this data the same way with an ampersand, right? You can access this just the normal way you would access 10 by saying the variable, and you can now access the data that it's pointing to inside of here, and you can do that a third way using the asterisk, which we'll show off here on line 28. All right. Any questions with this so far? Wait a couple more seconds here. Let me pull this up. A couple more seconds here to see if any questions roll in, and then we'll continue on with what's going on here. And while you guys ask questions, I'm actually going to modify this real quick so the printout is a little bit easier to understand. So my int is going to be, and then I want to do /t here, and then this is going to be my pointer int /t And this is going to be the ampersand my int slash t, and this is going to be my pointer int slash t. The variable, the value, the definition of the kind of value. So it's basically the variable, the value, the definition of the value, kind of, I guess, right? Yeah, kind of. Yeah, you can basically think of it kind of like that, because there's the variable itself, there's the value it holds, and kind of like where it exists. I guess you can call that the definition. And then the value it holds, depending on what type of value that is, you might be able to do extra things with it. Like if it's holding a new page in memory or a new location in memory you can go to that. So let's run this example here in the code and kind of see this with our eyes and how it works. So what's going on here, let me close this first. What's going on here is couple things. So one thing we didn't hit on, let me hit on it real quick. My int, we've seen in Python you can do plus equal 1, right? And that will add one value to my int, right? We've seen this before, we've done it in Python. In C, they have a way to do this even faster. If you just say my int plus plus, that means that you want to do the same thing. You want to add 1 to this variable, right? Hence why C++ was named C++, because it's a clever play on this, right? You can add 1 to it, so they're adding 1 to C. It's the next version of C. Get it? Ha ha ha. All right. So what's happening here is, look, when we access my pointer int, if we print out and want to access the data inside of my pointer int, it will take us to this data right here, this arrow that points to this data right here. Whoops, I should do a different color than orange. Let me do red. All right, it's going to point to this data right here, which means my pointer int, if we were to print that out, which we do here below, we'll see it, is going to print A, B, and C. It just says A, B, and C. To go to A, B, and C, the address A, B, and see the data inside of that, all right? That's the third thing I was saying we can do. We use the asterisks, all right? So that's why this is set up like this right here, all right? Let me remove this plus plus for right now. And we don't technically need these parentheses. When you do this, this means don't just, when you're going here, don't just stop here, right? Don't just stop here at A, B, and C. Actually go down the rabbit hole further, go to where A, B, C is, and then this is going to be our final destination, 10. So this is right now the value 10. Because we went to the pointer that we were holding, all right, and we traveled to where the value 10 is in memory, all right? We went through this address we had stored to the value 10. So the asterisk is to go one level deeper. Exactly. It's been a while since I watched Inception, so I wish I could use some Inception references, but that's exactly it. The asterisk is to go one level deeper. And that's actually probably the best way to do it. You can actually do as many asterisks as you want and go deeper and deeper and deeper if your pointer was pointing to more pointers that were pointing to more pointers that were pointing to more pointers. All right, we're only going one level deep, so we're only using one pointer right now. All right, so if we put these in parentheses, all right, this means resolve this first. You know, just like in math and in our logic in Python, sometimes we want things to resolve first. So we want this, you know, us going deeper and getting to this value 10 to be resolved first. Then if we do a plus plus right here, this is us saying the value 10, we want to add 1 to it. So 10 is now going to turn into 11. The thing is, we're changing the data right here. This 10 right here, which means that we're actually changing the variable myInt because we're changing the data it holds. So other variables can actually change the data of other variables using pointers. So you're going to see now when I run this that myInt is now a value 11. And if we print the value, one level deep of my pointer int, it is also 11 because both of these are pointing to the same data in your memory. All right, this is just the same right here. All right, it's one level deep. If we want to print the original my pointer int and its value, you'll see that the pointer, the table of contents version of myInt, is this value, this pointer value, and it's the exact same as this pointer value. So what does this all mean? It means exactly what we have here in our picture, right? It's exactly what we have here in our picture. Our table of contents here, so to look at the table, I guess I should add one more print here. Let me add one more print here. 1 second. Let's do ampersand my pointer int and ampersand my pointer int. Let's rerun this. There we go. So we can look here and see that, can I clear this up a little bit? Perfect. So ampersand, I think I can do this on snipping tools. Hold on. Let me grab this first. Grab this next. Copy. And paste this right here. Let's make it a little bit bigger. All right. So what's going on here is, why is this brushes? There we go. So we got myInt and we got my pointer int. All right. When we first declared these values, this is going to be in the same order: X on top, Y on bottom. So my pointer int is going to be the Y and myInt is going to be the X. All right. Ampersand is the value in the table of contents, aka this value right here at the top. All right, so this value is the table of contents value. All right, this is the location, the page. When we read the table of contents, it's the page that says where this is located, right? Where it is in RAM. All right, so that's what points us to right here and to right here. And you can see that this value is different than this one, right? They both have different table of contents. They both have different pages they live on, all right? Because they are both values, they're both variables that get generated. Just one holds an integer and one is going to hold some type of page number, right? Some type of memory location. When we print the actual value of myInt, it's going to say, it's going to say 11 right now, but imagine we didn't add 1, all right? Imagine we didn't add 1 to it, all right? So it's going to say 11 or 10 by default before we add 1, which is just like what we have right here. And this is in order, so we have to look all the way down here. This is where we're just printing the OG value of my pointer int. All right, when we print the OG value, we're not printing the OG value right here, but if we print the value of it, you're going to see it has this address stored inside of it. All right, it's going to have this address stored inside of it. Kind of like I said right here, it will have this address stored inside of it. When you want to go one level deeper, you can use the asterisk, which we use right here. All right, this little asterisk right here. All right, that's us saying go one level deeper and go to this 10 value. This is the same 10 value that my int is holding. All right, my int is holding. So when we add one, we're just adding one to this value that my int is holding. We made two variables that point to the same data. So the space savings for this is you can now share data very easily. You can share where it is in memory. You don't need to make new variables. You don't need to make temporary variables or as many of them. You don't need to duplicate your data in memory, which happens a lot in Python. You simply just pass the memory location and you can just have that one version of it everywhere. All right. Let's see. Kind of like letting you go into folders that's named. Yes, like folders, and like you can have shortcuts on your desktop, which are basically you click on that shortcut, which may look like a folder, and it actually auto redirects you to another folder. It's the exact same thing. It's literally the exact same thing. All right. This topic is this is for some people more complex to understand than classes. So hopefully you guys are catching on and this kind of makes sense. All right. Because it's very important for you guys to know this before we move forward. All right. But the whole thing is you can use this potentially to save on space. You can make smarter functions. Instead of you passing the data in to a function, when you usually do that, it will duplicate the data. So in Python, when you have a function and you pass data into that function, by default, it's going to duplicate that data. So if you had, a variable that was like a player and all the contents that player had inside of it, when you pass it to a function, you run the possibility of duplicating that and doubling the amount of RAM that's used to store that value. But in C, you can just pass a pointer to where your player lives in memory. And the pointer will only be of size 8 bytes. It will only be 8 bytes in size, all right? So you can just pass that instead of duplicating your whole player character, all right? So that's like one potential massive way to do a lot of, get these space savings, but there's also a speed performance thing. Because in Python, it may be duplicating that character in memory, then you may do some computations, and it won't update that character at all. It will probably return a value to you, and then you have to use that value it returned to do whatever updates you want. In C, if you pass a pointer to your function, it has raw, unadulterated access to that data. It can just change it immediately. Just straight up. It doesn't have to have you do any extra work, which we've actually already used when we were using scanf. It's kind of doing that behind the scenes. Because we're about to go on break. I'd see the time. Just want to get past this point real quick first. When we use something like scanf, is this, no, this one, here we go. When we use something like scanf, we're using pointers to our advantage here. Because remember in Python, we have to say input, and then we can put a prompt here, but we have to get what it returns. So user input equals input, and then we have to store that, right? So, which means inside of the input function, they have to also store that data and then return it to you, right? We're not doing that here with scanf because we're using pointers. We're effectively saying, hey, scanf, this is the address, right? This is the address right here, this A, B, and C. This is the address of where the data lives. feel free to change it however you see fit. So scanf will directly change that value for us on our behalf in memory. That is why we don't have to return anything. We don't have to do assignments afterwards. It auto-magically does it for us. All right. So that is the powerful benefit of pointers here. So we're going to go on break for 3 to 5 minutes. While we're on break, if you have any questions, please put them into the chat so we can talk about them, answer them, and then we're going to continue on with our talks here of pointers and ways pointers are very useful and how you've actually been using them automatically in lists and arrays. All right. All right. I'll see you guys in 3 to 5 minutes. Alrighty. We are back. Alright. We will continue our journey here. I did get a reminder. Alright. Susana reminded me that we have to do our drawing for participation. Our participation award. Alright. So what we'll do is excuse me, we'll roll just like the mystery gift to see what prize we're going to give away. And then we're going to roll to see which one of you guys will get the prize. How do we do this? How do you get entered to win? Well, you just chat. All right, just chat in the Twitch, YouTube chat, or the 100 Days of Rootkit Discord chat. You've been entered automatically. I know. So we do that once a month. All right, so I think there's only one more month. I think next month is the last month that we would be doing it for the 100 days. So make sure you chat and participating. We're gonna do the polling rewards for that at the end of today's stream. Right, at the end of today's stream. So let's continue on. Before moving forward though, if you don't know, if you're just tuning in right now, oh, well, this is quite a time for you to tune in, so I'll just say that. But if you don't know, we are Rootkit nonprofit here in the US of A. We do a lot of things for free, like 100 Days of Rootkit, where we teach you everything you need to know to get our comp sci cert and become a certified developer, skip college, skip any other boot camp. They're not even comparable. We're going to teach you everything that a college would teach you and more. All right. We're just literally ahead of everyone. It's absolutely insane. All right. So just watch these. Look, you're already watching right now. You're already ahead of the curve. All right. Next step, studying up, getting that cert. On top of all this free stuff we're doing, if you go over to blog, all right, we got the week 9 giveaway going on right now. So to enter that, you click the big green button and then just show that you've subscribed to our YouTube channel, following our Twitch, etc., etc. You have to do this every single week. All right, more free stuff. All right, participation rewards, free weekly giveaways. Honestly, we're kind of spoiling you guys. Maybe we should cut back a little bit. All right, because we are desperate for money. We are burning through money, probably with all these giveaways, to be honest. All right, we are burning through money like crazy. So in order to help us stay afloat, you guys can donate, and it's all tax deductible. Get those tax deductions. All donations are being matched 1-for-1 for the first 10,000 donations. Additionally, depending on how much you donate, you can unlock certain rewards like stickers, our Epic t-shirt, and this Epic sweater I got on here. Has a Rootkit logo on the back. 100 Days of Rootkit right here, a little special sticker. It matches our special exclusive 100 Days of Rootkit exclusive sticker here. Additionally, we have pillars along the way, like streaming for 24 hours straight, shaving my head here live on stream, and the goal that we don't want to reach is shaving my beard. No one wants to see that, so we're not going to reach it. All right, let us continue forward. I didn't see any questions, so hopefully everyone's being truthful here. All right, let's continue on. So pointers, we're starting to see kind of the benefits of them. They can potentially add space savings. They're being used in stuff like scanf to directly access variables and change them however they see fit. This can be, again, a huge pro, but if that sounds a little dangerous, like maybe a hacker would want to have that type of access, you're 100% right. All right, you're 100% right. So be careful what you guys are doing, and make sure normal users just don't have access to change data they're not supposed to. All right. Array magic. Let's go take a look at what this one's doing, shall we? So we have these things called arrays. All right. We should be very familiar with them. Remember, the difference between lists in Python and arrays in C is that arrays in C can only contain whatever value you've assigned to it. So if it was integer values, they can only contain integer values. All right. They can only contain integer values. Unlike lists in Python, where they can contain anything you want them to contain. All right. So this is just an array with 3 values in it. Nothing special here. We've seen this before. All right. Below that, oh, this is the new thing we talked about. We're making a pointer called second. And that pointer called second is going to be equal to my array plus 1. What? Wait a second. What is even going on here? That doesn't even make any damn sense. Array plus 1. Like, is that going to add 1 to the array? We'll see. We'll see. All right. So right below that, we're going to be printing out the value of array from position 1, which is going to be 110. Then we're going to print out the value of what we're storing inside of second. But not just the value itself, but the value of the value, all right, of second. Because we got that little asterisk there, which means we're going 1 deep, right? 1 pointer deep, which may be revealing that this is actually a pointer. We'll see. Then we're going to print the OG value of array, and we're going to print the OG value of second, all right? So let's go ahead and run this. Build errors. Did I forget a semicolon? What was the build error? Failed. Cannot open. Oh, let me close that. There we go. Alrighty, here we go. So if we look at this, we're going to see that, again, we're printing array of position 1, index 1, which is 110. And second here is also going to be printing out the 1 value deep, which is both 110. What is going on here? What magic is happening? Great question. So your array is actually just a lot of pointers. It's a lot of pointers, right? It's a bunch of pointers. So it's pointers that are following more pointers that are then pointing to data, right? Think of it kind of like laid out like a train, all right? So hopefully you guys don't want this anymore, all right? We're clearing it, clearing the board. When you make an array, 1, 2, 3, in C, what's actually happening is you're making a pointer value like you are here with second. All right. So this pointer value is going to, this is why you also have to hard define how large your array is going to be. So this one's going to be 3. If we weren't assigning the values right here, we would have to say definitely how large our value is going to be. All right. Anytime you're statically defining your variables, your array sizes, you have to be explicit. All right. You have to be explicit. You must know ahead of how large everything is going to be. Oh, but I may not know. You're right. You may not know. There's a solution for that. We'll get to it in a second. All right. All this is going to be in the stack. Stack starts with S. Static starts with S. Static code goes in the stack. Remember that. All right. It's important. So what's going to happen in memory is you're going to have, just like before in your table of contents here, you're going to have my array. I'm just going to write my, because that's a lot of writing. My array is going to have an address. Let's say it's A, B, and C. All right, this is going to point down to address location A, B, and C. Now inside here, there's going to be a lot of data right after each other. There's going to be pointer, so like your go-to basically, your go-to. So this is going to be a bunch of pointer addresses, one after one. In this example, it's going to be 3 because we have 3. So it's going to have a pointer that says 100 and A, 100 and B, 100 and C, because we have 3 values. All right. If you go to each one of these addresses, 100 and A, 100 and B, and 100 and C, these are all going to be different locations in RAM, which will contain the values of 100, 110, and 120. This happens in Python with your lists automatically. This happens with your arrays in C automatically. Just because you're in Python and you're not seeing these pointers, do not mean they're not there and you're not using them, because you are. They are there all the time. All right? You are there all the time. Oh, can't see what's behind my head. There we go. All right. So automatically you're doing some inception here. All right. You're doing some inception here, and it's happening auto magically for you. All right. So when you actually want to access value 1 in your array, which is going to be this value, you're actually looking up this, going here, and you're saying that you want value 1 right here, index value 1, and you want that data to be printed out. All right. There's a lot of magic that's automatically happening for you guys behind the scene. All right. This is what's happening. Now you can use that to your advantage and exploit it. Because if you get the contents, all right, if you want to print out the contents of my array, all right, it's only going to return to you 1 pointer value at a time, right? 1 pointer value at a time. So it's going to, by default, give you the item of index 0. So it's going to return to you this one. Oops, thought I clicked orange. If you do +1 on it, it's basically you shifting down and saying, just kidding, I want of item 1, index 1. If we did 2, it will tell us to get this item instead, which means we'll see 120 print out. So if I change this to 2, we'll see that 120 print out. And if I close my other one, 120 is now printing out. So it's effectively the same way as if we were doing it in this syntax and saying 2 or saying 1 or saying 0. So in C, you have multiple ways of accessing data. And it's important, if you're going to program in C, to know how data is laid out in memory and all the different ways you can access memory in C, because it could be potentially useful for you and you could potentially exploit it. All right. So this is why we're talking about this, because it's important to know how arrays are listed in memory. This is the same way it's done with lists in Python. All right. Any questions here? Any questions here? All right. This is not like insanely useful for normal use cases. All right. This is just something to show you guys data structure wise what's going on in your memory. All right. And all the places that pointers are being used. All right. Yeah, there's not most use cases you're just going to be saying this, all right? But who knows? You may need to do this to access data directly. I don't know. There's a million different ways or reasons why you may want to use this, and there's also a million different reasons why you never use this, all right? The point is to know that it's a thing that exists, and this is how you'd go about doing it, all right? Let's go on to the next item. Lists of lists. Oh boy, lists of lists. If it wasn't crazy enough, why is this one mad at me? Printf must be address of a string. We're gonna run it and see what happens. Yeah, we're good. Okay. What is going on here? What is this? Why are there 2 brackets? Why is this one 16? So many questions. Don't worry. Don't worry. We got the answers for you. To make a list in Python, let's pull up Python real quick. 100 days. Here we go. Let's pull up Python. Whew, Python, safe. Easy, right? Let's go back to Python here. This file's empty, so I'm just gonna use this as an example. To make a list in here, let me zoom in a little bit. you know, we say my list equals, and then I can say hello. Here, let me copy exactly what's over here so we have these things matching. And let me tab this down one and then press enter. All right, this is how we make a list, right? Makes sense? Not too difficult. Well, remember, there's no such things as strings in C. There is only chars. There's only characters. There's only characters. To have a word in C is a string of characters, aka an array of characters. So this, you cannot just do this in C, because to make a string by itself, if I say char my string, it will be like this. It's already an array. It's already an array, right? Because you have an array of characters. So to make an array that contains more than one string, we need to make an array of arrays. All right, an array of arrays. What does that look like? It's just this. So we got an array, and we have arrays inside of our array. Right? So 1, 2, 3. This is effectively what's going on, right? Except each item in here is going to be a string, right? So we're saying that we want strings, and each one of those strings are going to be up to 16 characters in length, right? Yes. Each one of these are going to be up to 16 characters in length. All right. So basically, the deeper you go, this will be the most inward items and the most outward items. All right. So this is going to be any length. We could have this as 3 since we have 3 items here, or we can just not define it at all and it will see the 3 here and auto shove it in. And then this is going to be how long maximum wise these characters can be. Remember, whatever value we put in here, it will always give each one of these that much data. Each one of these will be able to hold up to 16 bytes of information, even though we're not using them all. This is only using 5, plus 1 for the null byte. Remember that, all right? But we have up to 16 we can use. If we use more than 16, it's going to yell at us, all right? It's going to say, you can't do that. You went over 16. Technically 15 because you got to leave 1 for the null byte. All right. So you can then use that to print out your lists of lists. All right. So if we print my list, all right, it doesn't really like it that much and recommends us not doing it, because what happens is it's going to, it doesn't know, you're not choosing a specific item to print out. Right. We're not saying which item in our list to print out. But it will still work because, like I said, when you have a list, that will point to where that list is in memory, and it will just have address after address after address right next to each other there. So when we go to this address, by default, it's going to see that there's a value here. It's going to grab that first value and try to print it out. So it's going to print out hello. It's the equivalent of saying index 0, right? It's the equivalent of saying index 0 without doing index 0. You can see that squiggly line went away because it wants us to be specific. When we're not specific like that, bad things could happen. So it's not recommended for you to do that. But it is possible because of how the data is laid out in memory. All right. So I'll go and change this back to the 0 here, moving forward. We can see that we're getting the size of. We're getting the size of here next. You can see the entire size of our array is 48, right? It's 48 in size. Why is it 48? bytes in size? Well, that's a great question. Let's bring up our calculator here and let's do some division. All right. Each item in our array is 16 bytes in size, right? So if we do 16 times 3, because we got 3 of them, that's 48 bytes, right? So we can see exactly how many bytes of memory we're using. We can be very specific and fine-tune things here. So our entire size of our list is going to be 48 bytes in size. The size of an individual item is gonna be 16 bytes in size, which makes sense because we said each item is gonna be 16 bytes in size. And then we can get the size of how many items are in our array, all right, which is gonna be 3. And how we're doing that here is we're taking the size of our entire list, which is 48, and we're dividing that by the size of one individual item, which is 16. So now we know that it is 3 in size. There is no way by default in C to get the length of an array. There is absolutely no way. It just doesn't know that. All it knows is how large that memory space is, 48. All of this other context pretty much goes out the window. All right, pretty much goes out the window. This can be potentially an issue. In Python, we're spoiled because we can get the length of things by, if I can find it right here, I can get the length of this list by saying length of my list. There is special stuff going on behind the scenes to figure this out, specifically trackers. All right, you have a lot more variables you have to end up creating in C in order to track the size of things. You have to manually do it. You can't, there's no way to automatically get the size of things. You actually have to manually track a lot of this yourself. All right, so it's usually common in C code to see some type of thing here called like my unsigned int my list size. You'll see stuff like this. It's very common. And in here, this is where we would track that we have 3 items in this array. All right. It doesn't make as much sense when we're statically defining stuff because we already know beforehand how large this is going to be. This makes more sense when we don't statically define stuff, which we haven't talked about yet. So don't worry too much about that. Let's see here. And then we can see our first instance of a for loop here because we didn't show for loops in C, but we have a for loop here next that's going to go through every item in our list and print it out. All right, it's going to go over every item in our list and print it out. We didn't talk about for loops in their structure here in C. It's different than Python, but we'll talk about them later. All right, we'll talk about them later. Let's go here to the next example. And that's going to be malloc and calloc. All right, so that's pretty much it for pointers right now. All right, that's pretty much it for pointers right now. Any questions? Any questions? Let me pull up the Discord and see. Any questions? It's important for you guys to ask questions right now if you are not getting any of this stuff. So in memory, we have the stack and the heap. All right. There's also, text, BSS, a couple other items that we've talked about before. Make sure you know all of them. They will be on the exam. right? And make sure you know what gets stored where, because it's important. You need to know your memory layout. As a developer, you are putting things there. You should know where your things are going and how they get laid out, all right? You gotta be responsible like that, all right? So far we've talked about the stack. We've been statically defining things, and they go onto the stack. There's also the heap. The heap is there for our dynamically allocated items. What does allocated mean? Well, we've talked about this before. You guys should know this, but that's for reserving something. In this case, memory. We're reserving memory. We're allocating memory. When you start a program, most of it's going to load up in text. Anything that's going to be used, all right, like variables, are going to go to the stack, right? Variables are going to go to the stack that are statically defined, all right? This all happens when your program starts up. It will put it there, and there's no changing it. Once it's there for the entire life of the program being on. So if you're running a game, all those stuff will be there for the entire existence of the program. There's no removing them. There's no getting rid of them. They will just be there. If you make something like an array that wants to allocate, let's say, a gigabyte of memory, but you're not going to use it except for one part. So let's say we want this to use like a gig of memory. All right. I don't know if that's a gig or not, but you could say that when you run this, it's going to take a gig of memory, right? How many bytes are in a gig? Hold on, we gotta look this up. I'm gonna show an example. Bytes in a gig, a byte. It's a billion, right? So let's go do a billion. 1, 1, 2, 3, 1, 2, 3, 1, 2, 3. It's 100,000. There we go. 1 billion. So this is technically gonna be a little less than a gig, but this is a gig, right? We are reserving a gigabyte of space in memory when we run this program. When we run this program, we can do that. Why are you... Oh, God. It doesn't like that right now. Let's do a little less than a gig. Oh, still running. Let me close this. There we go. It's reserving all that memory. Actually, I don't even think we're printing this one out. Hold on. This is for lists of lists. It would be best if I ran this. Lists of lists. If I run this, there we go. Lists of lists is running. Let's bring up Task Manager. Please tell me. Oh gosh, it exited. Oh, we're using a lot of memory right now already. All right, well, there's some safety nets put in that you might have to avoid, etc., etc. But the point is, if you allocate a gig of memory, it will be allocated when your program first starts, and it's going to be there forever. There's no way to get rid of it. Even if you only need it for a second, all right? Maybe you only need it when the program starts, and then after that, you don't need it anymore. Right now, you're going to have an issue because it's just going to stick around. That's going to be a massive issue, inefficient. Your players are going to be mad at you if you're making a game, if you're making server products. Your customer's going to be mad at you because they're not, you're using up all their RAM, right? You're using up all their RAM. So the way to avoid that is by dynamically allocating stuff using things like malloc and calloc, and instead your variables will be created on the heap instead. Do programs developers intentionally set higher memory usage for apps that don't need that much? Yes, typically because they're amateur. Typically because they are making stuff and they don't know exactly what they're doing, or they're fat fingering things. There's a bunch of reasons, but it's usually a mistake or naiveness, all right? Or improper programming. It could be potentially a lot of stuff. But it can all be solved. It can all be solved. There's no reason. There's game engines and other stuff that are ridiculous on their resource load. There's some game engines that, for example, Snow runs the gaming community All for One, AFO. There's a gaming engine that they run for, what is it, Squad? I've never played Squad, don't know it very well. But their developers are pretty terrible. They're garbage. The game requires a CPU of 5 gigahertz or more in order to run the server. Why is it like that? Because is it really that intensive? You know, that hardcore of a game? It requires a server? No. It's because the developers on it are trash, and they made it very single thread heavy when that's the improper way of going about it. You should be making it multi-thread heavy. But they most likely started developing as not that good of a developers, and then they figured out too late that they were doing it wrong, but they dug themselves too deep. Maybe the game launched and they had people on it and they didn't want to set aside time to redo things and fix it. All right. And that's why you get crappy programs like that. It's a pretty common occurrence. All right. It's a pretty common occurrence because you usually learn things as you're going through it. The thing is, though, as long as the thing runs and people can play it, people can use your browser, etc., even if it is a memory hog, it might be a little annoying, but if it's usable, guess what? If it fits, it ships. Customers aren't going to care that much. They're going to care a little bit, but they won't care that much. Additionally, if you're making inefficient programs that may not be super memory hog, but you know you can make them better or more efficient, it doesn't matter. To a certain extent, it doesn't matter because you don't want to over-engineer your products. If it is inefficient, but it works, and it's not causing any issues for anyone, then it's fine. It works. All right. You can't waste your time being most optimal unless you're making a program that specifically is for being as optimal and efficient as possible. Do not waste your time on it. Do not waste your time doing that because you could be optimizing for forever. So to dynamically allocate things, because maybe you don't know the size of stuff. Maybe you don't know how much the user is going to input. Maybe you're making a program that allows the user to enter in some dialogue, maybe a question. Maybe you're hooking this up to something like ChatGPT, all right, where users can ask it questions, a dialogue, etc. You don't know how long those entries are going to be. A basic entry-level dev is going to use an array or a string, and they're going to say, 255 is large enough for most questions, right? Or maybe they'll say something like 1024 or 10,000, whatever. That's large enough. No one's going to type more than that, right? Maybe, but also your code is now less efficient because you're allocating all this data into your memory. The solution is going to be dynamic allocation using things like malloc and alloking or calloking. This is a way to create data on the fly and reserve it in your heap. All right, your heap is something that expands and contracts with the running of a program. So when you look at your task manager, for example, and you see that things are running here, and at first, let's say you have your browser open and it's using, maybe you have like 20% memory usage, but then you start playing a YouTube video and doing other stuff and you'll see that it scales up. It's scaling up not because your stack is growing, because remember, the stack is for the statically defined stuff. When you start Google Chrome, whatever is taken in your stack is taken then and there. It will not grow in size. What's happening is they are dynamically allocating data on the heap and it's growing in size, right? It's growing in size, and that's why you'll see your memory go up over time because the heap is growing in size. That means they're using mallocing and calloking, all right? Mallocing and calloking do the exact same thing, just slightly different. Mallocing will give you memory that you ask for in size of bits. If you want 8 bits of data, you can say malloc and then say 8, and it will give you 8 bits of data in the heap. All right. Calc does the same thing. Malloc, though, is insecure. Malloc will give you 8 bytes of data, and it will just give it to you how it is. Now, just like your file system, which we talked about in operating systems, your file system by default, when you delete a file, doesn't delete the file. It deletes the table of contents, right? Deletes the table of contents. The table of contents pointer stuff, remember, we've talked about that just now. It's used the same way with your data on disk, right? It's a reoccurring theme because it works really well and it's used everywhere in computer programming. It doesn't actually delete the data. It just deletes the pointer to it, the table of contents to it. Same thing in RAM. When something is closed, if I close my internet browser, if I close VS Code, it doesn't actually clear that RAM. It just clears the pointers to that data. It says, hey, this data is up for grabs. The trash is still there. We didn't clean up after ourselves, but it's there. All right. This can potentially be malicious. Malloc starts with an M. Think malicious. Calc and malloc work the same way. Malloc is the more malicious version because you are getting that data with the trash in it. If I am a hacker, guess what? If I know you're using malloc and you're using what you're mallocing in an insecure way, what I'll do is I'll flood the rest of your memory with my program. I'll open and close it a bunch so it just fills up all of that empty space with my bad malicious code in memory. And it will just be left there. All right, my trash will be just everywhere in the heap. All right. When your program runs afterwards, it may malloc ask for some data in the heap, and the trash will be left over everywhere. All right, because only the table of contents will clear itself, replace itself, etc. But the heap itself, the raw data, will not be replaced. So when you malloc, you could be potentially mallocing malicious code. And if you're not sanitizing it properly, you've been pwned. All right. Calc is the safe way to do stuff. Slightly slower, but it's the safe way. When you calc memory, it works exactly like malloc. You're asking for some memory in the heap, and it will automatically zero it out. It will automatically take whatever memory you get and be like, let me just clean that for you real quick. All right, here you go, buddy. All right, so it will automatically clean that memory space for you. So if you do something that's potentially exploitable in your code, you'll be safe because whenever you calc things, it will be cleaned up for you. All right, so use calc over malloc. So this is where pointers become very, very useful. All right, this is where pointers become very, very useful because when you malloc stuff, let's pull up our a new paint here. All right, when you have a integer, so we have my int, let's call it malint, right here, my malint. This is going to be a pointer integer, which means if we have our memory, all right, here in the top, all right, table of contents little area, it will say that malint, I'm just going to write mal. This can be found at address location ABC. This is just like all the pointers we've seen before. If we go to address location A, B, and C, we'll see in here nothing, but this can do go-tos because this can hold a pointer value, right? This can hold a pointer value. By default, it will have nothing in it, but we can store a pointer value in it. When you run malloc, this will ask your kernel, This will literally interface with your kernel of your operating system. So this happens slightly different depending on what operating system you're on, right? It will go to your operating system and it will say, please operating system, look, I've been loyal to you. I love you. All right. Please, can you spare me some memory? And the operating system will be like, how much memory do you want? My God. And you'll say, in this instance, 8 bytes, please. I want 8 bytes of memory. Your operating system is in charge of malloking and your calicking because it's a request to the kernel. All right. It will look in the heap and see if the heap can afford giving you that memory. If it can, it will carve out that memory, that 8 bytes of memory for you, and it will also record that location, right? Let's say this location is 1AC, right? 1AC. So when you malloc something, malloc will return a value to you, right? It's going to return a pointer to where this data was carved out, all right? So in this instance, malloc is going to return the pointer of AIC, and it's going to be stored inside of our malint variable. So inside here, we're going to store, it's 1 AC. 1 AC. So, congratulations. You've now created dynamic memory, right? You've created dynamic memory, and now you can store, you can store data inside of here. Any type of data you want, all right? So this is a combo step because you have to have something that is statically defined because you need to know your variables beforehand. Your variables themselves will be always statically defined, but you can make those variables pointers to data that doesn't exist yet. And then you can malloc or calloc, asking the operating system to then give you more data depending on what needs or needs not to be used. All right. And then you'll use that pointer to then point to that data that you can then utilize. All right. So let me there we go. And let's go ahead and run this example. Why are you giving me issues right now? Mallocing. Do I have it open? No, I don't. Let me run this again. Ignore get char, cannot convert. Where's this error at? Oh, am I even, let me delete this. I think I just wrote this down while I was talking. So let's go and run this. And you're going to see here some things printing out. What are you saying few about, Kamal? Are you okay? What's going on, man? All right. So let's look here. We are printing first the value of malint. The value of malint. We malloc this data. We requested it from the operating system. Please give me some data. Please. All right. Please give me some data. All right. And it gave us some data. So our request was successful. To prove that that data is dirty, it's dirty little data. All right. It's dirty when you use malloc. It's malicious potentially. All right. When we print out the value of that data, all right, because you can see the little asterisk right here, which means we're going deep, right? We're going one level deep. We're going to what this has inside of it. Inside of it, it's not going to be clean if you malloc. It's going to be dirty. It's going to have some leftover data in it. You can see here, we're getting some dirty numbers. All right. It's been a bad program. That's all I got to say. All right. You might be seeing this thing on the street corner late at night. It is dirty. It is nasty. All right, don't use malloc. You can see that we got some values here. You may think initially this might be the minimum for an integer value. It is not the minimum for an integer value. If we look up what the minimum of the integer value is, I guess we don't even need to look it up. We can just run that program or that function here for, oops, why are you doing this to me? What is going, are you kidding me? Is it because I'm gonna kill this thing. Why are you not letting me comment it? Why is my control not working? Okay, really? This is ridiculous. Can I just, there, oh, just undo. All right, if we print this out, variables again, you're gonna see here at the bottom, our integers. An integer's minimum value is this, -214 blah, blah, blah. All right, we don't need to memorize all this. We just memorize -214 is what it starts with. This is the minimum for an integer value. If we look at our mallocing here, remember, -214 is what it starts with. If we go over to our mallocing sequence here, we are mallocing an int's worth of data. I'll explain this stuff later tomorrow, all right? Because we're kind of running over time right here. If we run this, again, we didn't put any data inside of it. So if we run this, we can see we got dirty data. This is not -218. This is something else, completely different, because this data is dirty. We're getting the remnants of some other program in my computer. It left this trash laying around, and now we have it in our program. So make sure you use calloc, because calloc will automatically zero this out. It will automatically make everything null bytes, 0 bytes, all right? Null bytes just mean it's going to be 0 in binary all the way through, all right? It's going to remove all that trash. And here below, we can see the table of contents value of malint is this. And then we can see malint itself, which is going to be a pointer to that malloc data, is going to be this. You can see these numbers are quite a bit different, quite a bit apart from each other, all right? Because literally the stack and the heap are going to be on separate sides of your RAM, all right? The stack is going to be visually on top, and your heap is visually going to be at the bottom, all right? They're going to be on opposite sides of each other in memory, and they grow towards each other, all right? When you ask for too much memory in your, when you're mallocing, and if you are successful in doing it, all right, so your computer allows you to do it, and you're successful, when your heap grows too large and they collide with each other, that will be a heap overflow, because your heap is overflowing. Your heap is too large, overflows, and your program will crash. Your operating system may even crash. Vice versa will happen when the stack grows. So when you initially open a program and your operating system gives you more than it's supposed to, it will grow and hit and collide into the heap, and will do a stack overflow. There you go. The more you know. All right. There's also other ways you can do stack and heap overflows through inputs. All right. They're terminology that's used for several different types of exploits and bugs. That is one of them, all right? And this is why. They are physically, and you can see the address-wise here, you can see the addresses will always be separate from each other, all right? A lot of information to take in. Dirty little data. That's right, all right? It is a lot of information to take in, all right? It is a lot of information to take in. I'm not going to go into this too much more. We'll talk about freeing and what's going on here in a second. I'm just going to show... Wait a second, what the hell did I do? I'm not gonna even think about it right now. All right, calicking is the exact same as malacking. The only slight difference is when you say malic, you say just 8 bytes straight up. All right, calic takes 2 values, but it just does multiplication against them. So if you say 1, 8, aka 1 times 8, all right, 1 times 8, it's going to do the same thing as malloc. It's going to ask for 8 bytes of information, all right? So just think of it as multiplication, 1 times 8, all right? They do the exact same thing. One cleans, the other one dirty, potentially malicious. Which one's malicious? The one with the M, all right? We'll talk about and get into this more tomorrow, all right? We'll get into this more tomorrow. Any questions before we end the stream? We got to do our giveaway. So before we end, we're going to do our giveaway, then we'll end. How long does it take you to get as good as you are now? Or did you always kind of have a knack for it? No. I was very bad. The thing is, I'm slightly autistic, all right? I obsess over stuff, all right? And I'll go deep for days straight, little sleep, all right? You know, going deep down that wormhole, all right? So, no, I am not naturally good at programming. It took many, many years of self-teaching, all right? Some of these concepts I'm teaching you guys about right now, you guys are understanding them better than I did when I first learned them. Again, something like classes. It took me like a year at least to really understand what they were and start using them more properly. An entire year. Because I was teaching myself, and this was like in the middle of junior high, all right? So, and there wasn't the internet as you know it today. I was going to the library, getting books like this, and trying to read them. And books like this aren't really meant for junior high kids, all right? They're written for adults usually, all right? So, a lot of things going in. We're trying our best here to explain these concepts to you guys as easily as possible, visual aid, using it in games when possible, so you guys really can understand and get them in a dramatically shorter amount of time, right? Dramatically shorter amount of time. What was I going to say? If it takes you a while to understand this, do not feel bad. It's normal. If you're doing it faster than a year for understanding objects in classes, congratulations. You could be potentially a better dev than me in a shorter amount of time, all right? It's not really about time, all right? Because I've been doing this for over a decade, all right? Doesn't matter. You can be better than me and better than all of our staff members in half that time if you pick things up better, all right? If you have better teachers, better educators, better people helping you show the way, which is what we're doing. We want you to be better than us. We're passing the torch off to the next people that want to carry on. That's the whole point of education in the education system. And if the school systems or college systems that you're participating aren't doing that for you, well, that's normal because they suck ass. And that's why we exist. So we can do a better job for you guys and improve everyone's life, make companies more powerful with more powerful devs that actually understand things better at a deeper level. Because a lot of this that we're talking about right now will not be covered in college. You will not get exposure to this in most college classes. And I mean literally 90% of them. If you go to the University of Washington, if you go to the University of Colorado, if you go to any of the technical colleges in Colorado, they're not going to cover this topic for you if you go to computer engineering. All right? They just don't. How do we know that? We have friends and family that went to those, got their degree, and were not taught any of this. All right? And guess what? It's needed for a lot of jobs, at least to know about this to a certain extent if you're going to become a powerful, badass dev. Let's see. Okay, I'm in my university's last year, and you sort of are a YouTube professor, haha. Just here to watch while I munch on chips. Yeah, that's what. Hey, we're here to educate and certify. So if you're going to the university, look, you can get our cert in parallel with it. The thing the university won't do is really help you get a high-paying job. We will. If all of our cert holders, we will help you prep your resume. We will help you apply for jobs. We want you to get a high-paying job. So we will help you along those steps. All right. Additionally, things in our certs are going to teach you things that your employer wants. And colleges will not teach you that. Universities will not teach you that. They're going to teach you what the old hag that's teaching you wants you to know, which is going to be stuff from 10, 20 years ago when they first learned programming for 3 years straight and said, hey, I'm kind of shit at this, so I'm going to be an educator instead. All right. That's the typical path for most professors and educators in the world. All right. Not the best of the best. It's usually the worst that's going to be teaching. All right. So that's what we're changing to. All people that teach are required to be functioning within the job industry and cannot do it more than 3 years. You're required to go back and become a pro dev, and then you can come back and teach more because you're required to stay up to date. What's your take on Codex? Bro, I've been telling people forever to use Codex. So a couple, if you're just joining in from the stream, you missed our Codex example a couple days ago. I don't remember which day it was, but effectively use it. Use it. If you're learning coding, use Codex. A lot of people are hung up on ChatGPT. ChatGPT is jack shit when it comes to coding. Use Codex. It was literally made for it. Use it to auto-document your code, to explain concepts to you, to generate concepts for you. It's a powerful tool. Use it. You can even use it on our exam. I don't care. It's not going to help you make or pass the exam, all right? It might help you make a couple pieces of code. It's not that great though, all right? I've used it a lot myself. Use it though. It's a tool. Why wouldn't you use it, all right? I know it spits garbage for new questions, but a lot of coding is copying, pasting. Yes, it does spit garbage sometimes, but so does Stack Overflow, all right? Stack Overflow has lots of garbage code on it, all right? So, I mean, it's the same thing people are going to say like for Wikipedia. Wikipedia is a great source for information, straight up. Anyone that says otherwise is living in the old days because they're going to want to say encyclopedias. Guess what? I issue encyclopedia. Those are infactual a lot of the times. And there's a reason why they come out with new encyclopedias every single year to fix the mistakes, except they must stick around for a year. Wikipedia can be updated immediately. Wikipedia is the superior product and should be used as the ground truth for most of what you're referring to. It is as reliable as an encyclopedia. All right. Same thing with Codex and Stack Overflow. Before Stack Overflow, you'd be referring to people, trial and error, looking at books. Books don't have the latest and greatest things. New versions of C, Python, etc. will come out. You will have to buy new versions of this. You're also trusting that the person that made this book knows what they're talking about. That's not the case a lot of the times. All right? They may not be the best person in the world. They may not know what they're talking about sometimes, but they'll still spout it and put it in a book. It costs nothing to write a book and publish it. Anyone can do it. You just got to find a publisher, or if you're using Amazon now, you can just publish for free, basically. Stack Overflow came around, which was a great alternative because it's live. You can get down specific to the new version. You can immediately get feedback for new stuff and for any new tools, niches, etc., etc. Codex, not 100% yet, but it will get there. It will be a superior alternative to Stack Overflow because it will be knowledgeable in everything and it will be able to give you, right now it does a pretty good job. It will give you the answers for most of your questions So you don't even have to mess with Stack Overflow. But the thing is, it can do even more than that, which is very, very impressive. So I would give it a couple more years, but Stack Overflow I could see becoming just not even needed anymore because Codex is just going to be so much superior. Maybe it's not Codex that wins out. Maybe it's some alternative, but regardless, a Codex-like system is going to win out. It's not going to replace any developers. It's not even close to that good. All right, it's not even comparison. All right, but it may be eventually in a good enough state where it can make most programs. I mean, the same argument's been done for website development. Website makers like Wix.com and Shopify, or what, Squarespace, they've come a long way, but it's not going to be like they're not taking over and replacing every website because you still need developers at the end of the day. Same thing for the AI stuff. Any other questions? All right, you guys can ask your questions. We're gonna go ahead and do the giveaway while you guys ask any last minute questions here. So if we go to the 100 Days of Rootkit, just to show, so we're gonna first roll which item we're gonna give away. So we got all the stickers, the 100 Days of Rootkit stickers, the shirt, and the sweater. All right. So 1 through 4. Again, same as before. Top one's 1, 2, and then 3, and then 4. So let's do random number between 1 and 4. Now it works this time. So 2. We're doing another sticker drop. All right, another sticker drop for the winner. And Susanna said we have 1 through 86. So let's choose 1 through 86. 64. Who won, Susanna? Who won? So if you guys are just joining us now, so if you're not tracking, at the end of every month during 100 Days of Rootkit, we give a participation reward. All right, it's a random merch item of ours, which we just pulled for. It's going to be all the stickers. And it goes to anyone that's potentially been chatting in the YouTube chat, the Twitch chat, or the 100 Days of Rootkit Discord chat. All right, so number 64 is going to win. So Decisions has won. Congratulations, Decisions. I don't know what your Discord tag is. Decisions in here, let me tag. Is he even here? Decisions. No, he shows up in the YouTube chat. So we'll be on the lookout for him. I don't remember what his Discord name is. So if someone remembers that, let me know. Yeah, because am I spelling Decisions correctly here? No. Yeah, no, he's not in there. What does 64 have to do with Decisions? Oh, so every time you leave a message, it's being logged. So out of 86 messages, or it's not a message, so every day that you leave a message, your name gets logged. All right, so out of all the days, there were 86 people's names logged in total. So we were drawing a number between 1 and 86. So someone's name in regards to there. And then, so whoever's was 64 wins. So every day that you're here and you're participating, you get a new entry. Susanna I think she's typing right now to explain a little bit more. But there's just a big spreadsheet. Yeah, he was number 64 on the list. Yep. So I don't know what day that was, but whatever day was encompassing that, I mean, I would imagine, yeah, in order of days of chatting, I list who chatted. And we just did all of February. So this is not including January. This is just for February. So it's starting all over again. So today is the first day of this month. So everyone that's chatted today in the Twitch chat, the Rootkit chat, or in the 100 Days of the YouTube chat or 100 Days Rootkit chat, your names have already been logged on the list and you've already been entered in the new giveaway. If you don't want to wait till the end of the month, remember, you can go to our website. And if you go over to blog, you can enter into the week 9 giveaway. All right, week 9 giveaway. So at the end of this week, we'll be giving away another random item. Any other questions before we end today's stream? Because that's all that we're going to go over today. assignment-wise, challenge-wise, just mess with the pointers. Just mess with them. See what you can do funkiness-wise. All right. Tomorrow we're going to go over malloking, calicking, and strings, dynamic strings, and more calicking. And we're going to go through these examples of our super secret math algorithm, right? And then we're going to also talk about memory. I think this will just let us do memory profiling, if I remember correctly. Where we're talking about memory profiling. This is a concept that you can do in Python. It's not just C exclusive. I'm going to wait another couple seconds to see if there's any other questions before we close out today. Oh, look at that. Decisions is here. So you'll opt out? All right, let's re-roll. Susanna, go and re-roll. Or wait, I re-roll. Decisions has said he's good for the merge, so we're going to re-roll random number between 1 and 86. 83. Who's 83, Susanna? Kamal, you better have emailed me. I don't see an email from you. I swear to God. Is it him again? All right, I'll re-roll. 71. Decision's just the RNGesus, I guess. he's like Evox. Oh wait, it was Kamal? No, okay. If go back to the 83. If that's Kamal, then 83 won. I thought you were gonna say that 83 was Decisions again. Okay, so if 83 is Kamal, then congrats, Kamal. You've won more stickers, all right? Oh, you were building tension? Oh, I thought you were just like angry. All right, Kamal, you've won more stickers. You better email me, all right? You better email me back because you have a lot of merch you need to claim here before it goes bye-bye. All right, I'll get you the hoodie, all right? You got to email me still, though. You still have to email me. Yeah, I emailed you first already. It's going to be eharmon@rootkit.org. All right, I put it in the 100 Days of Rootkit chat. I tagged you in it. Yeah, eharmon@rootkit.org. All right. All right, sweet. That's all I got for you guys today. So I will see you guys tomorrow on the next one.